Hey guys, welcome back. Today we're going to be talking about metamorphic rocks. Metamorphic rocks are the third type of rock. We've covered igneous rocks, sedimentary rocks, and now this will be metamorphic rocks. And remember, they're all connected together in a thing called the rock cycle. We haven't really emphasized a lot of the rock cycle in this class because it's implied when we talk about metamorphic rocks and igneous rocks and sedimentary rocks that they had to come from somewhere. And they just came from other kinds of rocks. All right, so with that said, I just got to lead off and say that metamorphic rocks, compared to the other types of rocks, I have to admit my favorite are actually sedimentary rocks. I like igneous rocks a lot. I think they're fascinating. I actually really love sedimentary rocks. I like hiking through the Grand Canyon and all that. But the prettiest rocks of all are metamorphic rocks. Metamorphic rocks are amazingly beautiful. You get a wide range of amazing textures and colors and crystal types and mineral types. And sometimes they pop up in places you don't expect anything to form. So with that said, let's go ahead and start talking about metamorphic rocks. So there's several kinds of rocks right here actually. This is a rock called a metamorphic schist. Don't worry about it. We'll cover all these things. There's another rock in here called a banded gneiss. This actually is almost slightly melted at some point to something called a migmatite. This up here is marble. Marble is metamorphic limestone. And of course, here we see another type of rock which is quite famous. It's called a banded gneiss. Really beautiful rocks ahead. So what is metamorphism? Well, metamorphism means to change form. It's simply the transition of one rock into another by temperatures or pressures unlike that which it formed. Changes in mineralogy and sometimes chemical composition. So you get both. You get not only the rock type changing, but the minerals, the chemical composition, but you also get a whole different texture. This rock down here is a banded gneiss. It's a beautiful banded gneiss. But in this case, the parent rock, or the rock that metamorphosed to form this, was actually a shale. Really cool, because you would never look at this and say this used to be a shale. It's completely different, and it's a very hard rock. Shale is real brittle, fissile, tends to break apart really easily. All right, so every metamorphic rock has a parent rock. So the parent rock in this case is the shale. Parent rocks can be igneous, sedimentary, or even other metamorphic rocks. And to really understand why different rocks form at different stages in metamorphism, for example, if you have what they call a low-grade or a high-grade metamorphic environment, you get different kinds of rocks forming, even though they all might have the same original parent rock. So metamorphic grade is the degree to which the parent rock changes during metamorphism. It progresses from low-grade, low temperatures and pressures, to high-grade, high pressures and pressures. So here we see a low grade, high grade up here, and here we see, for example, a case of shale being metamorphosed. So during metamorphism, the rock must remain essentially solid. So it's not allowed to melt. That's kind of the rule of metamorphism. If you melt it, it's no longer a metamorphic rock. It becomes an igneous rock at that point. So the rule is that it cannot melt, or else it becomes classified as an igneous rock. So here we see a shale. And if you recall from previous lectures, shales are made predominantly out of clay minerals and quartz, and those clay minerals and quartz are actually formed from the weathering of other types of rocks, predominantly igneous rocks, through the rock cycle, right? But if you put it under low-grade metamorphism, in other words, add a little heat and a little pressure, shale will alter into a type of rock called a slate. And a slate sees that these clay minerals alter from kaolinite and things like this into things like chlorite and muscovite. Now muscovite you'll remember from the igneous rocks. So muscovite turns out is a relatively low grade metamorphic mineral, and it forms with chlorite. But quartz, notice down here, is pretty persistent. But the other thing that's really cool is that when you form shale, remember the clay minerals form at the expense of the feldspars. Feldspars tend to break apart, and not just the feldspars, but most of the mafic minerals as well. But look, when you go from shale to slate, the feldspars come back. So it turns out feldspars are a relatively high pressure, high temperature mineral. It doesn't form on the Earth's surface. All right? And then when you transition from slate, you can transition over here to a phyllite. Phyllite meaning layered, or actually the word the word phyllite actually means to be like paper thin or to be layered. And one of the reasons why is because some of the important minerals are biotite and muscovite in a phyllite. And biotite and muscovite tend to be very, very platy minerals. But also because the rock takes on a platy texture to it. So slate is very famous because it's used in chalkboards. and makes that nice surface. Phyllite gets a little more flaky as you're going forward. And you start seeing things like garnet, a mineral called kyanite, which I've not mentioned yet, but feldspars and quartz will continue to persist all the way up into the highest grade until you literally melt the rock. And then, of course, two other types. Schist, spelled S-C-H-I-S-T, and it's not pronounced schist, which is a very different word. Schist is a common rock type. Another one is gneiss. This is G-N-E-I-S-S. Both of these have origins that are not in English, so you want to make sure that you pronounce them correctly, otherwise you get a really bad term coming out. So what do these rocks look like as we go into increasing grade and pressure? Increasing pressure and temperature. So here we've got our shale, which is really low grade. As a matter of fact, it's not metamorphosed at all. But we go from our low grade zone to our high grade zone. And just as you bury the rock, it goes from slate, here's a schist, here's a gneiss. And if you get too high a grade, you actually start to melt the rock. So an extremely high grade type of metamorphic rock, where there's actually melt coexisting with the rock itself, both existing at the same time, is a rock called a migmatite. So here we've taken a shale and we've cooked it all the way to a migmatite, and it's actually starting to transition into an igneous rock at this point. But this is under standard burial metamorphic temperatures. You can get other things where you temperatures and grades. But if you come up here, you'll notice that there you can get rocks that are at very high temperature but very low pressure. And then down here we have very high pressure but very low temperature. And this is a blue schist. These are really common, but they're really beautiful rocks too. And we'll talk about the origins of these shortly. So what drives all of this? Well, of course, heat. Heat is the most important agent, or one of the two important agents. And recrystallization is the process of forming new stable minerals larger than the original. Two sources of heat. There's the geothermal gradient, which, just as you bury rocks. An increase in temperature with depth, which is about 25 degrees centigrade per kilometer, or Celsius. Contact metamorphism, rising mantle plumes, for example, bring rocks, molten rock, right up in contact with cold rocks up near the Earth's crust, up in the Earth's crust, actually. And so that's contact metamorphism. It's like putting a blowtorch right on the rocks. Okay? Confining pressure. These are forces that are applied equally in all directions. So when you're down below, say you're, maybe you're diving, you can feel that there's water coming at you from all different directions when you dive down into the water. The same thing happens with rocks. As you go down into the Earth's surface, you get pressure pushing you in all directions, and it's trying to compact you into a small zone. And basically what that does is it causes the spaces between mineral grains to close up into smaller zones, or even completely close up completely. Differential stress. So this is when you just have regular confining pressure, but you can also get situations where the forces are unequal in different directions. So stresses are greater in one direction. This would occur like in a fault zone, where the stress is tending to take things in one direction at the expense of things in another direction. Okay? Compressional stress. Rocks are squeezed as if in a vise, gravity pushing down all that rock down below. And it's shortened in one direction and elongated in the other. We'll see examples of that as we go forward in this lecture. Here are these concepts in a diagram. Undeformed strata right here. You'll notice that the pressure is coming in all directions. Same thing here with the deformed though. Here we put a lot of confining pressure down below. So the rocks up here are at much less confining pressure than we see down here. And so here's a high confining pressure. So the same rocks here take up less space here. They're compacted. And of course, during mountain building, rocks subject to differential stress are shortened in the direction of maximum stress. So in other words, you're taking this set of rocks over here and compressing into this set of rocks here. So if it was undeformed, as we see up here, and you compress it, it starts to look like this. And you have a huge arrow of compression this way and this way, but the other arrows are much smaller, showing that the direction of impact is this way. Another really important component of metamorphism is the release and migration of chemically active fluids in rocks. So we tend to think of rocks as being these dry things with no water in them, but water is pretty typical. And this tends to enhance migration of ions. It aids in recrystallization of existing minerals. In some environments, fluids can transport mineral matter over considerable distances. So here we see basically a rock up here and a rock. It's the same rock, but we can actually see a zone of alteration where water was flowing through here and distributing ions of different types, metals and potassium and things like this all throughout the rock, and taking it to, in this case, probably a distance of about a mile away. So to really understand metamorphic rocks, you actually have to really have a good understanding of what the importance of the parent rock is, because without understanding the parent rock, we don't really know enough about the chemistry of the rock. So to see where things are going, you have to know where they came from, is basically what we're saying here. Most metamorphic rocks have the same overall composition, chemical composition, as the original parent rock. Very similar, I should say. If you were to break it down, dissolve it down in acid, it's pretty close. The mineral makeup determines the degree to which each metamorphic agent will cause change. So mineralogy is really important. It's a reason why we spent so much time covering minerals and chemicals. Chemistry, I should say. Texture describes the size, shape, and arrangement of mineral grains. Metamorphic rocks can display preferred orientation of minerals in which the platy minerals exhibit parallel to subparallel alignment. So texture is extremely important of the protolith. Cool, so unlike other types of rocks, igneous rocks and sedimentary rocks, which have structure, the metamorphic textures and the metamorphic structures are extremely interesting all the way down to the microscopic level. I mean, you can pick up an igneous rock and you see the vesicles and you can see the big phenocrysts, and it's beautiful stuff, without a doubt. Same thing with sedimentary rocks, looking at all the different mineral grains and seeing how they distribute themselves throughout the rock. But metamorphic rocks have a totally different way of arranging themselves, and it builds up on the molecular level all the way out to the rock level. So in this case, we're going to talk about foliation. Foliation describes any planar arrangement of mineral grains or structural features within a rock. So here's some examples of foliation down here. Here we can see nice, it almost looks like layering. This is a metamorphic rock. This is a metamorphic shale that has been altered into a slate. And this is due to parallel alignment of platy or elongated minerals. So platy minerals, think of muscovite. Parallel alignment of flattened mineral grains or pebbles. So think of maybe a rock like a conglomerate or a breccia that's been squished. Those grains will be all squished out. It'll take on a preferred orientation. Compositional banding of dark and light minerals is pretty typical. As a matter of fact, we can see that in one of the slides below. And cleavage, where rocks can be easily split into slabs. So here we can actually see that cleavage, that rock cleavage everywhere. This is a slabby piece down here. All this stuff down here and up in here is all broken off. So, but over here we can actually see that parallel arrangement of platy or elongated minerals. So this is quartz all through here, this black and white colored stuff right through here. But the stuff that is in blue and orange right in front of you, these nice long platy minerals, this is in all probability muscovite. And muscovite, as we know, is a phyllosilicate. It's something that is, it's a platy mineral, very, very platy. It also has a little bit of water in it, which is kind of important to keep in mind. But here we can see that texture extends all the way from rocks like this, these slates, all the way down to the microscopic level where we can see individual crystals of quartz and muscovite all in nice wispy bands. Okay, here's a nice thick band of quartz right here and a kind of a more muscovite rich zone right in here. So foliation can form in various ways. And we just kind of introduced some of these things, but the rotation of platy minerals, so you can have a bunch of minerals like this, and you start to squeeze it, and look, it develops a preferred orientation. And so this might be the way that you get this type of rock transforming into this kind of rock. Okay, recrystallization that produces new minerals perpendicular to the direction of minimum stress, or maximum stress, I'm sorry, which is what we saw in the previous slide, and flattening spherically shaped grains. Okay. In fact, here's a sphere. Imagine that, you squish it and it's going to take on that shape as well. Here we see another example of this, solid state flow, where we have a mineral grain and the preferred orientation of stress is straight up and down. And so to accommodate this and to squish out of the way, the quartz crystal in this case, say this is a sand grain, quartz sand, it starts to shear. Now remember that quartz doesn't have really good cleavage. It has very poor cleavage. So what it'll do is it will take literally the crystal lattice up here on top and just start offsetting it, moving it over. That takes a lot of energy to make that happen because quartz does not like to break. Okay, but over enough time, with enough pressure and enough heat, in fact, it will devolve into this thing, or evolve into this thing, I should say. So here we see the flattened rock containing elongated quartz grains right here. And the pore space is still preserved, but eventually even that will get filled in with enough pressure and time. So here we see some rock and slaty cleavage. So the rock can actually break just like slate. This is exactly slate. And this is where rocks split into thin slabs and develops in beds of shale with low-grade metamorphism. So this is a low-stage metamorphic shale called a slate. And here we can see some excellent slaty cleavage. This is actually on top of a roof. I believe this is a roof of an old barn or shed in Scotland. And it's several hundred years, about 350 to 400 years old. It's several hundred years old. It's excellent as a building material, but in the event of an earthquake, you wouldn't want to be underneath this thing. Fortunately, not many earthquakes in Scotland. They do happen, but they're very small. All right, the next kind of cool thing to look at is stuff called schistosity. Unfortunately, the picture that I have down here is a little pixelated, so we'll kind of breeze past it, but we'll show you better pictures of schist as we go forwards. Platy minerals are discernible with the unaided eye, I should say. Mica and chlorite flakes begin to recrystallize into large muscovite and biotite crystals. And actually, these little white areas here are large muscovites. That's what these things are here. The black zones are little biotites that are just starting to form in here. And they exhibit a planar or layered texture. And rocks having this texture are referred to as a schist. So this is a schist. Another type of foliation is this gneissic texture right in here. Okay, notice those bands of dark and light minerals. So during high-grade metamorphism, ion migration results in the segregation of minerals into light and dark bands. Remember, the light bands tend to be more felsic. The dark bands are probably a little more mafic, if we're thinking of this in terms of igneous terminology. So we have more mafic minerals, which means iron and magnesium. Over here, we have more silica and potassium in these zones here, and maybe sodium, quartz, and potassium. And although foliated, gneiss do not usually split as easily as slates and schists. So this is a lot of people look at this as almost like it's a granite in terms of its hardness. It just doesn't seem to want to break. So you can pick this piece of rock up, you can hit it, and it will break in almost any orientation. So there's another really cool set of textures that we need to kind of quickly talk about. First off, not all rocks are foliated. We make that assumption, but they're not all foliated. And this tends to develop in environments in which deformation is minimal. Get my pointer back, minimal right here. So you're just basically burying it, and the confining pressure is kind of the same everywhere you go. So you don't really get a preferred orientation in that case. And of course, you can also get porphyroblastic textures. Porphyroblasts are kind of like phenocrysts. Phenocrysts have these, remember, are those big crystals that form in a ground mass of smaller minerals, let's say in a basalt, where you have a big olivine crystal sticking out of the basalt, but you can't see any other crystals because they're too small. Well, the same thing is happening here. Here we see a schist, and in that schist is a new mineral that we have not discussed before. These are garnets. So garnet actually tends to form, not always, but usually form in in metamorphic rocks. Over here, here's a slide from a microscope, and here we can see biotite. That's that darker orange mineral. The quartz is forming nice layers. Biotite is forming nice layers. But right here in the middle, this is a big garnet. This is one of these garnets right here. Maybe that's a lot smaller than these, but anyway, here it is. Here's a garnet. You'll notice that the muscovite is actually swirling around. And the reason why is because and you can actually see the S shape inside the garnet. The reason why this happens is because the garnet has actually been rotating while the rock was forming. And that's because the rock, while it was forming, was under some type of differential stress. So as a consequence, things are kind of moving along and the garnets were forming at the same time. So here's some common metamorphic rocks. We've kind of been hitting this all along, but let's kind of just do a quick review. Here's a slate, and this is the kind of the texture you get. Phyllite, you still get that nice slate kind of linear texture, but notice that you start to get a different kind of wavy feature in here, right? And so the parent rock is usually shale or mudstone. Here's a schist. And so these are all foliated rocks, gneiss right here. And so this all has the same parent rock. It's all a shale. You can also get gneiss from granite or certain kinds of volcanic rocks, but it's usually shale. And then, of course, down here, non-foliated rocks, we find marbles, which are derived from limestones. We haven't spent a lot of time talking about that. Quartzite, which is the metamorphic form of quartz sandstone. And these are actually really common, turns out. And then hornfells, which is often shale but can have any composition, and they're very fine grained, exceedingly tough and durable, and usually dark colored. This is one of the ugliest rocks on Earth, if you ask me. So we have some of the most beautiful rocks up here, and probably the ugliest one down here, one of the ugliest, right next to Gray Wacky. All right, so let's start covering the individual rocks themselves. Here we see a slate. This is kind of a rehash, but slate, which is very fine grained, has excellent rock cleavage, and is usually generated from low-grade metamorphism of shale, mudstone, or siltstone. So here's a typical example of a slate. And we've seen this, like I said, in elementary schools nationwide, possibly worldwide, chalkboards made out of slate. So when they write up on there and you hear that distinctive sound, know that they're writing on a slate chalkboard. A phyllite is kind of the next grade up. And here we see there's actually still that kind of that layering that is indicative of a slate, but notice it's bended. These little ridges and runnels that are run through here across the top kind of indicate that this is a phyllite. Also the fact that it's kind of shiny. And the reason why it's shiny is because we start seeing rocks like, or minerals like muscovite and biotite start forming in here. So the degree of metamorphism is between a slate and a schist. So schist is the next one. Platy minerals are larger than slate, but not large enough to see with the unaided eye. So you see that sheen, that nice sheen coming through here that's turning it into a lighter color. The glossy sheen and wavy surfaces, and it exhibits rock cleavage. Cool. Foliated rocks. Here we see schist. This is a muscovite schist, which is a relatively low-grade schist, but it's still a pretty neat schist nonetheless. Parent rock is shale, believe it or not. It doesn't look like shale anymore. That has undergone medium to high-grade metamorphism. The term schist describes the texture, right? The texture of it, not necessarily the minerals. Platy minerals, mainly micas, and I should say muscovite and biotite are the two main ones, predominate. And it can contain porphyroblasts. If you guys remember the garnets were actually forming in a schist a couple slides ago. And of course, here we see kind of the penultimate of metamorphic rocks before you start to melt them, which is a gneiss. And these are medium to coarse-grained metamorphic rocks with a banded appearance. You can actually see the crystals here. There's no doubt you can see crystals in here. The result of high-grade metamorphism. It's composed of light-colored feldspar-rich layers with bands of dark ferromagnesian minerals. So neat stuff right here. But you'll notice those foliations coming through here. But you can't really break it. It breaks just as easily down the sides as it does across the top. Or almost as easily. So here's another one that we haven't spent a lot of time talking about. You have to go back to our discussion of sedimentary rocks, actually, to understand marble. So marble is a crystalline rock from limestone or dolostone parent rock. So if you remember, limestone and dolostone are both carbonate minerals. Limestone is calcium carbonate, dolostone is a magnesium calcium carbonate mineral. The main mineral in marble, however, is calcite. So you can metamorphose dolostone, but you lose a lot of the magnesium when you do it. And as a consequence, it's a pretty soft rock, right? It's a 3 on the Mohs hardness scale. Remember, quartz is a 7. 3 is pretty soft. It's used as a decorative and monument stone. And the impurities in the rock provide a variety of colors. Here we can actually see some impurities in this marble. You can actually see the grains of marble. But we got bands of red, bands of white, or little zones of white, I should say, in here. And of course, we got a zone of gray to bluish gray, if you will. Cool. Cool rock. And one of the neatest rocks, actually, is quartzite. This is a rock I love to look at. So quartzite formed from a parent rock of quartz-rich sandstone. And quartz grains are fused together in these things, right? So here we have a quartz sandstone. Here we see this is what the grains look like. We can remember that this is what they look like from our discussion on sedimentary rocks. But if you recall, as we put pressure and heat to these things, the pore spaces close up and the minerals start to fuse together and they get preferred orientation. And when we look at it close up, it looks like this. Okay, neat. So iron oxide may produce reddish or pink stains. This has definitely got iron oxide. Here's an iron oxide vein in here, and it's going to stain the final rock pink. And dark minerals may produce green or gray stains. So you might convince yourself that you see a little bit of, in the smaller area, little zones of dark green, possibly. And then hornfels, of course, we just talked about this earlier. Hornfels, the parent rock is usually a shale or clay-rich rocks. And when I say shale or clay-rich rocks, remember clay-rich is an indicative of a gray-wacky. So hornfels sometimes is thought of as a meta-gray-wacky, which is one of the reasons why the hornfels is not the prettiest rock in the world, because the gray-wacky is probably the world's ugliest rock. Baked by intruding magma bodies. So this is where you come in and you just heat the sucker up with contact metamorphism. So I just brought up an important word or term, contact metamorphism. So that leads us into our discussion of metamorphic environments. What brings about metamorphism in the first place? Okay, so here we see two kinds of rocks over here. One up here is a banded gneiss. We can see that it's nice. It's got a nice texture right here. And then here's another one where there's a vein of molten material that probably came through here. But if we look here, there's little chunks of rocks sitting in what looks like a rock that had melted at some point. So this is in fact one of those migmatites I was talking about, where it's partly melted. And what it has done is the lighter stuff is melted off, the darker stuff actually had melted at a higher temperature, so it could actually take the heat. And so you had a zone of both right here at this location. And later on, dikes and sills would come in and fill it in with more felsic stuff that flowed in. We actually see a similar pattern over here. This is actually also a migmatite. And through here, we see the light zones were very, very fluid. We can actually see the way it's cutting through here, right here. And we'll notice that there's these white veins that are cross-cutting the rock everywhere. That means that they had to come last stage, right? There's kind of a rule in geology, which is you got to make it before you can break it. So the rock had to exist, but still there was molten material that was filling in these veins. Neat. What brings that about? So there's types of metamorphic environments. There's contact metamorphism. This is where you bring a heat source very close to the cold rocks. In this case, you would experience a relatively low pressure, but a very high temperature. It's like putting a blowtorch on something. And so we call this contact metamorphism. All right. You can just bury rocks. That's one thing, burial metamorphism. But if you bury it so far, actually in this zone, this is still really diagenesis. But once you get down into this zone down here, you get regional metamorphism. And regional metamorphism is where you're just so far down that everything starts to alter under metamorphic conditions. And then if you take things to too high of an extreme, the rock actually starts to melt, especially if the temperature gets too high. Okay, so this is a pretty wide zone in which metamorphism occurs. And of course, the swath of metamorphism actually expands out as we get further down because it's harder to melt rocks under extremely high pressures. So here is a really neat map that kind of explains contact metamorphism pretty effectively, I think. So contact or thermal metamorphism results from a rise in temperature when magma invades a host rock. It occurs in the upper crust, which is low pressure and high temperature, we just described that, and the zone of alteration or an aureole forms in the rock surrounding the magma. So here we see a granite. Remember, granite is a big plutonic body. Big igneous body. And when this granite came in, it intruded something called country rock. This is the protolith, or the parent rock of the metamorphic rock. And as a consequence, we have cold rocks here, very hot magma chamber that was here at some point, and we would see a zone of metamorphism between the two. And sure enough, we've gone through, geologists at some point and have mapped this out and have mapped out the metamorphic aureole that goes all the way around the granite. So this would be a zone of metamorphic rocks. And the kind of alteration we get is kind of predictable. You know, we have an igneous granite here. Out here we'd see our maybe bands of shale, sandy shale, some sandstone, limestone. And what would we get as we get close to the igneous granite? Well, in the case of the shale, it's going to go to a muscovite chlorite. That's going to go into a slate. And then you're going to see the biotite and andalusite. That's going to be closer to a phyllite into a schist. Cordierite sillimanite, I haven't mentioned cordierite and probably won't mention it again for the rest of the class, but that's a high pressure, high temperature mineral, or actually a very high temperature mineral. And sillimanite, these tend to form in gneisses and schists as well. And of course, then you can just really cook the heck out of it. Very high pressure, a very high temperature hornfels, actually very high pressure, or high temperature. That same zone actually connects all the way through here. So the shale, the sandy shale, this shale, all alter to the same types of rocks right in this zone. But notice a limestone will go from a fine-grained marble to a coarse-grained marble into another kind of rock that I'm only going to briefly mention called a skarn. A skarn is a rock that is a blend of silica and calcium carbonate right along the contact between the igneous granite and the limestone. And skarns are actually a pretty good indicator location for minerals like gold. Igneous rocks tend to be well, I'll just leave it at that. I don't want to get into the chemistry too much. And then, of course, sandstone will alter into a quartzite. And as you go from this dashed line over here, the sand grains and the degree of metamorphism will increase until you get right along the igneous granite boundary, in which case the quartzite is going to have well-developed and very large crystals with very little pore space. So here are some examples of this exact thing happening. This is a magma chamber that intruded into some country rock, and some of that country rock is still up here on top. Now, since the mountains have gone up and exposed the pluton, that top of that country rock is still up there on top. It hasn't eroded off yet. Fortunately, it hasn't eroded off yet, so we can still go and see them. And so this was the old top of the magma chamber. This was the old roof of the magma chamber. And so these little features are called roof pendants because they're still hanging up here on top of the magma chamber. And we can see this zone, this transition zone, in this case, this is from the Sierra Nevada. There's another roof pendant down here, and I believe this is in the Utah desert somewhere, where we see a pluton that has come in, and there's a roof pendant sitting up here on top. The same degrees of metamorphism that we've been describing are exhibited at these locations. Another way that you can do massive alteration of a location and a little wider zone, while it's still associated with a magma chamber, is through metasomatism. And metasomatism really just means hydrothermal metamorphism. So chemical alteration caused by hot ion-rich fluids circulating through pore spaces and rock fractures. This is really common along the axes of mid-ocean ridges. So here we see, here's a magma chamber down here. We've got layers of rock up on top that are probably basalt. And what happens is the cold seawater is going to enter here, and then convection is going to pull this water that's down here and push it straight up out along the axis of the mid-ocean ridge. So the cold water enters and it exits right here. So we get a plume of hydrothermal solutions that are distributed all along here. And basically that hot water is just scrubbing out all kinds of ions and altering the rock and forming all kinds of great metamorphic rocks in the very center of that zone. So here's the black smoker actually in action. Here we can see some biological activity, but here we see all that hot rock, which was drawn in from the ocean some distance away, is now being expressed right here at the mid-ocean ridge. And I believe this is in the Atlantic, if I can recall. But these types of things also don't just happen in the mid-ocean ridges. They also happen on land too. Geysers do this, geysers and hot springs. So here's a geyser that's active. And basically, it's a hot water geyser, and the water down below is circulating through above a magma chamber. The magma chamber occasionally produces so much heat that the water down below turns to steam while the water up on top is still cold. And so as that pressure builds up from that steam, eventually it overcomes the confining pressure of the water above it, and it blows the water out the top. That's what geysers do over time. But every time it does it, it distributes minerals all around here, and so you can see a nice platform of mineral deposition that has occurred around this geyser, even right around the edge of the geyser where it's really extreme. And then usually the water will then circulate, in some cases, right back down into the geyser again and then recycle itself every couple of minutes, hours, days, or however often the geyser erupts. But it doesn't just have to be from water that falls from the sky. It could also be from water that comes from magma chambers itself. There's a huge reservoir of water actually still in the mantle. It's working its way out of the mantle up to the Earth's surface. And so this is actually magmatic water that's coming out. This is not steam from this lake here. This is actually water coming from a magma chamber at depth. And what does that do? Hey, it creates our rock veins that we love so much. We can see, here we see a nice quartz vein coming through here, but across the quartz vein is an even lower temperature mineral, gold. So this is a gold vein that is being deposited into a metamorphic rock. Really beautiful picture, actually. Burial metamorphism is really neat because if you bury things and you get it to the point where it's not completely recrystallized, you can actually preserve old structures. So here's a sandstone, and here you can see the crossbed still preserved in it. Here you can actually even see the direction of not only the water movement or the wind movement in this situation. I don't know whether this was laid down by water or by wind, but you can still see the crossbeds, and you can actually work out that stuff. Really neat. All right, so there's another place where we get a lot of metamorphism of a different type. Besides the burial metamorphism and the contact metamorphism, we get subduction zone metamorphism, which is a type of very high pressure but relatively low temperature metamorphism. So sediments in oceanic crust are subducted fast enough that pressure increases before the temperature can adjust to it. So here we see a model of, in this case, this is the temperature of the rocks with respect to depth in this direction. So this is the depth, 800 kilometers. And notice that through subduction, you get a plume of cold rock that actually gets descended way down into the Earth's crust. In this case, this rock is only 800 degrees. And if this was rock at the surface, quartz would barely be melting at this point. Okay, but it's right adjacent to rock that is 1650 degrees Celsius. So this is a really hot rock right next to a really cold rock. And so these rocks over here are undergoing metamorphism, let's say in this zone, that is high pressure but relatively low temperature. And so this is what we see here, rapidly subsiding or subduction right here. And so this gives us our rocks called blue schists. Now we also need to bring up this idea of pressure, temperature, time paths. That's kind of implied by this, right? That in this situation, the pressure increases before the temperature does, and that gives you this path right here. In contact metamorphism, it's the opposite. You get a high temperature, but the pressure doesn't really increase that much right away. By the way, this is the zone of partial melting. So once you get in here, you start actually melting the rock, and you get things like migmatites and even igneous rocks forming from that. So let's go back to this pressure, temperature, time pass. Here we can actually see a rock that would be under extreme pressure and heating would actually hit its maximum pressure before it even hit its maximum temperature. So this would be our zone of peak metamorphism right here. So here we have prograde metamorphism, where the rock is being buried and heated up and under very fast pressure, burial. And here we can see that eventually it's going to decompress and cool as it makes its way up to our surface. Otherwise, we will never see that rock, right? It gets subducted forever. And so we can map out the pressure and temperature time path as this goes through. And here's another explanation of this: burial, heating, exhumation, which means where it's being brought up back to the surface through exfoliation or mass wasting or tectonic processes. And of course, regional metamorphism is the last of the kind of the types of metamorphism we need to talk about. So these produce the greatest quantity of metamorphic rock, and basically these are associated with mountain building and the collision of continental blocks. So here we've got a continent moving in one direction, another continent coming here. Imagine this is Asia, India. You bring these two masses together, you form the Himalayan mountains. But what do you get in terms of rocks? Well, right on the front of the mountains, you'll still see your slate. But the slates at the same rock layer, as you're descending through this whole zone, it's going to go from slate to phyllite to schist to gneiss. But it's the same rock. It's the same rock. It's just simply changing grade as we go along this zone of subduction. We also get a lot of metamorphism along fault zones, right on the fault itself. It's a great way to actually measure faults. These occur at depth and high temperature. So, if the rocks are too close to the surface, they're just going to break. They're not going to melt and swirl around and do some really beautiful things, as we see down here. So it has to be in a ductile zone. It can't be in the brittle zone, which is near the surface. So these are deep subduction zones, or I'm sorry, deep fault zones. So pre-existing minerals deform by ductile flow, and these types of rocks are called mylanites, and these form in regions of ductile deformation. So here we can see the rocks are literally flowing past one another. This would occur down in our deeper surface. Here we see a €1 coin, which is about the size of a quarter, and maybe a little larger if I can recall. And here we can actually see the rocks are moving through here. And you notice that this band is bending around the garnet here. This is a garnet right here. And that's because the garnet is actually spinning while one side moves one direction, one side moves the other direction. We can also get impact metamorphism, and this is something that that is developing a lot of interest in the scientific community. Not necessarily for studying the origins of the Earth, well, in some respects the origins of the Earth, but really looking at landscapes of other planets. There's zones of metamorphism that tend to develop as a consequence of these impacts, and certain minerals also form. So impact metamorphism occurs when meteorites strike Earth's surface. And the product of these impacts are fused fragmented rock plus glass-rich ejecta that resemble volcanic bombs. They're called impactites. Here's an impactite right here. These rocks look a lot like regular igneous rocks here on Earth. They're very hard to find. They're probably everywhere. We just don't know where to look for them. Here we see this is an impactite. I don't know where this was collected, but you kind of get the idea of the texture. And here's a meteor impact zone in Arizona. This is Meteor Crater, Arizona. This is one of the places you should put on your bucket list of places to see, so you could say that you've been to a real live meteor impact site. So we get different kinds of minerals, even in quartz. Quartz is probably the best one to look at because quartz is so common here at the Earth's surface to see what the different phases are. And so using what we know about metamorphism, it turns out quartz changes into different phases based upon temperature and pressure. So alpha quartz and even beta quartz, which are really common to us, we know what these look like. We're accustomed to them, especially this alpha quartz. We recognize that if we keep something here at the Earth's surface, it's all going to be alpha quartz. But as we increase the pressure to 2 gigapascals, which is a lot of pressure, by the way, we start to create something called coesite. Coesite is a phase of quartz where it's a polymorph of quartz. It's still SiO2. It's just a different crystalline structure. But scientists have actually discovered an even higher grade or higher pressure form of quartz called stishovite. Stishovite, of course, the name kind of implies it's a Russian name. It was discovered by a Russian scientist, I believe, in the 1940s or 50s. Anyways, you can look it up if you're interested in stishovite. Stishovite is a very, very rare mineral and only occurs in, you guessed it, meteor impacts. Very high pressure, very low temperature. Incidentally, as we go the opposite direction, we keep things at low pressure, we go too far this way, we actually start to melt the silica in the opposite direction. So you get the idea of how this works. So where do we find shocked quartz? Well, one of the places that we find shocked quartz, other than in obvious impact sites, is we can use it to look for impact sites. So here is a zone of where we see a bunch of sedimentary layers. Some drilling went through, and what they started discovering was that below a certain layer, there was a whole bunch of breccia. Remember, breccia is broken rock that is created by some type of event. And this is in Chesapeake Bay. So Chesapeake Bay became interpreted as an impact site. And what they did was they started looking deep into this hole, into this breccia, to see what minerals they would find. And sure enough, they started finding stishovite. So now, it's kind of common knowledge in the scientific community that Chesapeake Bay is, in fact, an impact site. There's a meteor that actually hit here, a meteorite impact right here. And notice the size of this thing. It's 50 miles wide. It's a very large impact. And it extended all the way down into the crystalline basement above the sedimentary beds. So anyway, just try and demonstrate that this is stishovite up here. Another place where we find stishovite is Chicxulub Crater. Chicxulub Crater is actually a crater that we cannot see. We can see it using geophysical methods, which I haven't taught you yet. And hopefully we'll have time in the class to be able to do it. But here we see Chicxulub Crater in the Yucatan Peninsula of Mexico. And in that crater, sure enough, we find the edge of the crater in a trough. We can actually see this using geophysical means. And when we looked around here, sure enough, we find stishovite. This is a block of stishovite right here. The date, using sedimentary records, by looking at the different layers and being able to look at the fossils and some other stuff, dates to about 65 billion years ago. This is almost exactly the same time that we see the extinction of the dinosaurs. So the interpretation by a lot of geologists and paleontologists, for the matter, is that Chicxulub's event, which generated this huge crater right here that extended all the way into Yucatan, if it didn't cause the extinction of the dinosaurs, it at least triggered the extinction of the dinosaurs, because within a short period of time, dinosaur remains are no longer found on Earth, and we enter the age of the Cenozoic, also known as the age of mammals. Okay, so neat stuff, and this is some shocked quartz from that event. But these things happen all the time. You know, this is a meteor that exploded in the skies above Russia. It actually, some people were killed. I don't know if they were killed by the rocks themselves, but they certainly were killed by some of the blast effects. And this thing came through the atmosphere and exploded in the sky. And it was much larger. The explosion itself was, you know, was like an atomic bomb or two. It was a fairly large rock, and they wound up getting samples of it. But these things happen all the time. There was another event earlier in the 20th century, also in Russia, that wound up leveling huge zones of trees. And if it had happened to hit a city, it would have vaporized the city. So these things happen. Meteors impact all the time. So let's go ahead and kind of wrap this up. Let's talk about index minerals. How do we know whether or not we're talking about something of high grade or low grade? We just look at the minerals itself. Shale, of course, being the most common sedimentary rock by far, is the best way to, you know, kind of analyze this and kind of work all this stuff out. So here we see shale. Shale tends to be transitioned to a slate, into a phyllite, to a schist, into a gneiss. We've kind of covered this several times now. But here are the index minerals. We know that we're in the slate zone when we have chlorite. And then chlorite will transition into muscovite. And if we look at biotite and garnet and starlite and selimanite, now you might be asking yourself, well, big deal. So if I have selimanite, I have a gneiss. If I have biotite, I have a phyllite or a schist. Well, we have to actually look at the assemblage of minerals. And we can get a pretty good idea of the metamorphic grade. So for example, if we find chlorite, muscovite, and biotite, we know that we have a zone that only extends between, where all three of them have to overlap. So in this case, it had to form somewhere between the phyllite phase here and the phyllite phase there. So only phyllites, by the definition of this chart, would experience chlorite, muscovite, and biotite all together in the same rock. However, if we found garnet, biotite, muscovite, and chlorite all in the same rock, we can narrow it down to just this little zone right here. And so one of the things that igneous petrologists, remember, petrology is the study of the origins of rocks. Igneous petrologists would use this to be able to figure out the intermediate grade, or the grade itself, of that rock. Chlorite, muscovite, biotite, garnet, schist in this case. What if it's a garnet selimanite schist? Well, then we know it's going to exist in this zone from here to here. So it's going to be a lower grade, lower half of the high grade gneiss zone. But if we find starlite and selimanite, then we know that it's going to be in this very narrow range down here. Okay, so we got, yes, one more image I want to show you. So if we heat things up too much, or we add too much, or we don't have enough pressure when heating it up, we wind up with a rock that is partially melted. And that's what this is right here. This is a rock that is partially melted. The white zones right here are the felsic minerals, the black zones are the mafic minerals, and the transition between these two, or the difference between these two, is that the white zones have lower melting temperatures. And so these were liquid at some point, whereas the black stuff was solid. And so this is the transition to igneous rocks. And we see a repeat in that rock cycle. All right, so with that said, I hope you enjoyed this little discussion on metamorphic rocks. I think they're genuinely some of the most amazing rocks on the Earth. And in microscope, they're absolutely dazzlingly beautiful. I could spend hours looking at these things. All right. If you have any questions or concerns about anything you saw in this presentation, by all means, send me an email or meet me on the messaging boards. Until next time, bye.